Hi everyone, this is section 6.3 in grade 12 advanced functions. This lesson is on transformations of log functions. Your homework is found on page 338 in your textbook, and you're going to have a short PT performance task, performance assessment in about 2 lessons time. So when we look at transformations of functions, it's actually the same principle. And we just apply these rules to a different type of function that looks different or has different characteristics. So when we take a look at the parameters equation, y equals to a log k times x minus d plus c, the parameters a and c affect the y value, the y direction or vertical direction, and the parameters k and d affects the x direction, x parameters. And the real meaning stays the same as what you already know. So when a is greater than 1, the absolute value of a is greater than 1 is a vertical stretch. If a is between 0 and 1, it's a vertical compression. And if a is negative, you reflect the graph of the function in the x-axis, so it's an upside down reflection. The k value, when we think about the horizontal parameters, we know that we have to use reverse logic. The absolute value of k1 is greater than 1. It is actually a horizontal compression by a factor of 1 over k. So I'll give you an example of this. If k is 2 in the equation, now we have a horizontal compression by a factor of 1 over 2. So that means all the points on the function on the graph will be half the distance closer to the y-axis than the original graph, okay? When absolute value of k is between 0 and 1 is a horizontal stretch by a factor of 1 over k. So for example, if k in your equation is 1 over 4, so now 1 over 4 is now 4. So that means every single point will be 4 times as far away from the y-axis now. And if k is less than 0, you reflect the graph in the y-axis. So it's a left-right reflection. The value of d, well, since the equation written here is x minus d, so if I substitute a positive number here, say 2, x will be minus 2. So this shows a translation of the units to the right. But if d is a negative number, so if I substitute a negative number in this expression, I will have x minus a negative number that turns into x plus the number, which makes a translation d units to the left. And then c, it affects up and down translations. If it's positive, you move the graph up. If it's negative, you translate the graph down. Putting these parameters into the mapping rule, you will get your very familiar, hopefully, expression of 1 over k times x plus d, comma, ay plus c. So let's apply transformations to the graph of y equals to log x. Well, I know that the graph of log x is base 10. So the key points that I can use can include log of 1, which is 0, and then log of 10, which will be 1, right? Because log of 10 to the power of 1 base 10 will give me 1. Well, what's the next key point? The next key point, we will have to wait until 10 to the power of 2, which is 100. So that's why this graph is increasing very slowly, because your graph only goes up to 15. So this graph, if you continue to extend it, it will reach 2 when x is equal to 100, okay? Also remember that the graph of log x is the inverse of an exponential function of 10 to the power of x. So if you remember the graph of exponential functions, they actually have a horizontal asymptote along the x-axis when you graph that. Well, now because we're flipping the x and y, for any log function, the graph will now have a vertical asymptote, and the basic graph has the vertical asymptote at x equals to 0. So using this fact, we will try to graph y equals to 2 log x. Well, the 2 outside of log x tells me this is a vertical stretch by a factor of 2. So that means any point on the original function is now going to have a double distance away from the x-axis. But zeros will not be affected. The mapping rule of this can be written as x comma y maps onto x comma 2y. So this point stays the same. Vertical stretch does not affect the position of the vertical asymptote, so it's still at x equals to 0. And then at 10, we used to be at 10 and 1. Now double that distance from the x-axis, we're at 10 comma 2. Next, we have the graph of y equals to log x minus 2. So the negative 2 is outside of the log function again. So this is a vertical translation of 2 units down. The mapping rule looks like x stays the same and y minus 2. So if you compare the graph of log x, you move every point 2 steps down and 2 steps down here. The vertical asymptote has not changed, and this is your graph. Next, you have y equals to log 2x. Now this time the 2 is written right next to x, meaning that this is a horizontal compression by a factor of 1 over 2. Remember to reciprocate this. When I do a horizontal compression, there is no change to the original vertical asymptote, so it's still x equals to 0. But now every single point is half the distance away from the y-axis. So we went from 1, 0 to half comma 0, and then we went from 10 comma 1 to 5 comma 1. And remember we said that the next point on the original function will be at 100. So now the next point is technically 50 and 2. Okay. The mapping rule also reflects the fact that x is now half the distance from the y-axis. Then you have y equals a log of x minus 4. Again, the change is occurring with the x. So this tells us that this is a horizontal translation. X minus 4 here in the equation tells us we're actually moving 4 units to the right. So the mapping rule shows x plus 4. This particular transformation does affect the position of the vertical asymptote. So don't forget that now you have to show the shifting from x equal to 0 to x equals to 4. And then for your key points, we went from 1, 0 to 5, 0. We also went from 10, comma 1 to 14, comma 1. The last graph here is the graph of y equals a negative log of negative x. So we have a double reflection. The first negative is reflection over the x-axis, is a vertical reflection. And then the second negative sign is the reflection in the y-axis, is a horizontal reflection. So from 1, 0, we come to negative 1 and 0. From 10 and 1, first we reflect vertically, so 10 and 1 becomes 10 and negative 1, and then reflect that horizontally. We're now at negative 10, negative 1. Okay. So let's look at a more sophisticated example when we have a combo of transformations. Now your base function is log base 10x or log x. We want to sketch the function negative 3 log of negative 2x plus 12 minus 4. Remember to factor k, then we can read the transformations from left to right. So -3 gives us a vertical reflection, stretch vertically by a factor of 3, reflect over the y-axis. The 2 tells us it's a horizontal compression by a factor of 1/2. X minus 6 means we're moving 6 units to the right. Minus 4 means we're moving the graph 4 steps down. Putting this into mapping rule, we get x over -2 plus 6, comma, -3y minus 4. Your parent function is log x, so the key points are 1 and 0, 10 and 1. There is a horizontal shift, so the VA, the new vertical asymptote, is also moved to the right 6 steps. Okay, so apply your rules, and then you get your 2 other key points so that you can make this graph. Now to answer the questions at the bottom of the page, you find the domain and range. So when you look at the graph of your function, it is to the left-hand side of x equals to 6. So that means all the x values belong to real numbers must stay less than 6. But the function continues forever up, and the function continues technically forever down. Okay, we're just very slowly going down, but it is going down. So the range is y belongs to real numbers. The function, if you scan from left to right, is always increasing, right? It's always going up. When we ask for increasing interval, we always read from left to right. So basically, it's the entire domain that gives you the increasing interval, and the function never drops, so there is no decreasing interval. The next set of questions asks you to find the positive interval, negative interval, x-intercepts, and y-intercepts. By positive interval, we mean that the part of the graph that stays above the x-axis. And by negative interval, we're talking about the part of the graph that is below the x-axis, but not including 0, right? Because 0 is neither positive or negative. So how do we find that? Well, I think the easiest way to do that is for us to figure out where the x-intercept is. So to find the x-intercept, you have to let y or f of x itself equals 0. And then, so plug in 0, put in your equation. We are trying to isolate x here. So first, -4 goes to the other side, 4, divide by -3. To get rid of the log, you have to write this in exponential form. So you have 10 to the power of -4 over 3 equals to -2x plus 12. Solve for x, it's about 5.97. To find the y-intercept, you plug in 0 into the formula, to the equation, and then you can use your calculator to evaluate. -7.238 is the answer. Okay? So that's this question. Here we have to sketch the graph of y equals a log x minus 2 base 2 plus 1. You start with the graph of log x base 2. If it's difficult for you to come up with the points, remember this is just reversing the 2 columns of the graph of 2 to the power of x. And then the mapping rule, we're shifting 2 to the right, 1 up. Here are the points, and here is your graph. And then the equation of the inverse can be found by reversing x and y. Okay, and then simplifying. And then the next part in your notes shows how you can sketch the graph of y equals x plus 1 base half minus 3. Parent function is this one. Use the points and half to the power of x. Switch the column, apply the rule, and graph. Okay. Thanks for watching.